Hey everybody, in this next video lesson, we're going to talk about trends in nuclear stability, and we're also going to take a look at calculating half-life of decompositions of unstable nuclei. First, let's take a look at this picture. This is one of my favorites from this chapter in the book. Across the bottom, we have atomic number, or number of protons, and then up the vertical, we have number of neutrons. And so basically, every time you see an intersection of a protons with the neutrons, if there's a blue dot, that represents a stable nucleus. And so you can see all these blue dots represent stable nuclei or stable isotopes when you have that combination of protons and neutrons. And then all of these yellow ones are a combination of proton and neutron that is unstable. And so you can see that at, like, say, for example, 10, there are two very small dots that have stable nucleus with 10 protons, and one has 10 neutrons, and the other has 11 neutrons, but there's a bunch of isotopes that have more neutrons and a bunch of isotopes that have less neutrons when the atomic number is 10. And those are unstable isotopes. So this line here in red represents the 1-to-1 neutron to proton ratio. And as you can see or remember, we talked about how when the elements are small up to 20, the proton to neutron ratio in a 1-to-1 ratio is stable. And you can see the blue dots falling along this red line. But then as we get into bigger ones, the blue section, all of these blue isotopes veer away from the 1-to-1 neutron to proton ratio line. This blue region in among the yellow or orange is known as the belt of stability, which are representing all of the stable isotopes of elements. And all of the orange ones obviously are off the belt. So we've got to the right of the belt, to the left of the belt. You can also consider it below the belt and above the belt. And I've got a couple of them pointed out here, like stable isotope of oxygen with 8 protons and 8 neutrons, or stable isotope of iron, as I mentioned already, has 26 protons and 30 neutrons. Take a look at these bubbles in yellow. Number 1, anytime the nuclei is above the belt of stability, to the left or above the belt of stability, the dominant decay is beta emission. Remember, beta emission takes a neutron and turns it to a proton. And so basically when beta emission happens, it shifts to the right or increases the atomic number and decreases the number of neutrons. So if you have an isotope that's above or to the left of the belt of stability, it will go through beta emission to shift right and down. Now, on the other hand, if you're below the belt of stability or to the right of the belt of stability, what you're going to do is you're going to do the opposite of beta emission. You're going to do electron capture or positron emission, because what those do is they turn protons to neutrons. So let's say you're one of these very unstable nuclei over here, just to the right of the belt. Well, when you do an electron capture, you shift to the left, becoming smaller in atomic number and increasing your neutrons. And so you're shifting left and up. So to get to the belt of stability when you're to the right, you go to the left and up using positron emission or electron capture. And if you are to the left, you'd use beta decay, which would shift you to the right and down. And then finally, number 3 up here are all of those unstable elements above the atomic number of 84. The dominant decay for these, as I mentioned previously, is alpha emission, because what alpha emission does is loses protons and neutrons. And what that does is gets us down to the stable belt of stability. That would be this blue region here. So if you are any one of these isotopes way up here in the upper right-hand corner, you're not going to do beta or you're not going to do electron capture. You're going to do alpha, which drops you to the left and down until you eventually get down into a stable nucleus that has less than 84 protons. Now we're going to talk about half-lives. And regardless if you're doing alpha decay or beta decay, electron capture, or whatever, half-life is still the same. It means, just like it did back in kinetics, the amount of time that passes for half of the original sample to be reacted. And in this case, reacted means decay. So let's say, for example, you have a natural isotope of like uranium-238. Let's say you have 100 grams of it. How many years would it take to go from 100 grams of it and decay through alpha decay down to 50 grams of it? Well, it looks like it's 4.5 times 10 to the 9th years. Notice all of these are in years. Other ones, you got uranium-235 or even carbon-14. Carbon-14 is a known radioactive isotope of carbon, and it takes 5,715 years for half the original sample to decay or change into something else. In this case, it changes into a different element using beta decay. So it's always considered a first-order reaction. always. There's no second order, there's no zero order. First order reaction rates when it comes to radioactive decay. And if you're going to use the integrated rate law, then you're going to use the one that has natural log, like I have highlighted right here. In order to solve for half-life, you take 0.693 over K, and that will equal the half-life. Or if you want to know K and you have the half-life, you can take 0.693 over the half-life to equal K. But either way, it's always first order, and the first order calculation for half-life, if you know K, is 0.693 over K. Consider a practice problem like this one. It says the half-life of strontium-90 is 28.1 years. How long will it take for 11.0 grams of sample to decompose to 1.00 grams of sample? Well, one half-life would bring it from 11 down to 5.5, and the next half-life would bring it from 5.5 down to 2.75, and the next half-life, so on and so forth. But we'll never get a nice round even number at 1 gram using half-lives. So we're going to have to use the integrated rate law to solve for this one. But we will need to use the half-life in order to solve for K, the kinetics constant, using the 28.1 years. Remember, 28.1 years is equal to 0.693 over K, and if I rearrange this, K is equal to 0.693 over 28.1. In that case, K is equal to 0.0247 years to the negative 1 power, and that's my K value. Now what I'm going to do is I'm going to take that K value and I'm going to stick it in here. I'm going to take the grams of sample and I'm going to stick it in for time is 0. That's the 11 grams. And I'm going to take the 1 gram and stick it in for A at time t. So once I do that, I punch this into my calculator and I solve for t because it's asking for how long or how much time in years. So I divide by the negative K value on each side, and t equals 97.2 years. And that is how I solve, using the half-life formula to find my K, and then I use the integrated rate law to solve for an exact amount of time. So be prepared to be able to use the half-life formula to be able to solve for a K value, and then use the K value to stick into the integrated rate law to solve for the missing time. Or you could do things in reverse. You could use this formula to solve for K, and then just plug it in here and figure out the half-life. If, let's just say you didn't know the half-life, you could solve it. If you're given starting and ending amounts of substances, you could solve for the K and plug the K in here and solve for the half-life. Well, that takes care of this video lesson. Thanks for watching.